We're going to skip phase for now because I want to get to the part that might help you think about the exam. Let's do that. We'll get back to phase when we get back. Okay, because here's what I want you to know for these problems, but also for the exam it might help. So once you have x of t, you have everything. Okay? Right, so if I now can write down an equation for this motion, I can do it all. Right? So let's write it down. Let's say our guess was correct. A sine, we could even get technical and put k over m here, t plus phi naught. Okay, I'll tell you how to get a and phi naught next time, but for now, just don't worry about them. Well, I could also write down the velocity. This is the position at a function of time for all times. I could also write down the velocity for all times just by taking a derivative. Oh, let's go back to calling it omega. But, well, okay, it's fine. Derivative of sine is cosine, and we take the derivative of this with respect to time and pull it out, right? So it's a square root of k over m cosine square root of k over m t plus phi naught. So now I know v. Let's see. So what else would I want to do? I could know the acceleration at all times. Okay, the derivative of cosine is negative sine, negative. We pull this out twice. It becomes k over m because we pulled it out twice, right? The square root of k over m squared is k over m. And then it turns us back to sine. So with those three, I could write down any expression you want. Right? What if I want the momentum? What if I want the momentum as a function of time? How would I get it? I would say, oh, the momentum is a function of time. T, oh, it's mv, right? I say a m square root of k over m cosine square root of k over m t plus phi naught. And I could start combining things and realize that's actually square root of km if I wanted to. You don't have to write this part down. I'm just giving you an idea, right? So now I know the momentum is a function of time. Okay? But now let's think in terms of this exam. You might think, now wait a minute. Is this momentum constant? No. Right? Here we have a case where momentum is changing, and momentum is supposed to be conserved. So what's going on here? Well, the spring is applying an external force. It's doing external work, or in the case of momentum, it's applying an impulse to the mass. Right? So it's okay that the momentum changes. But what if we tried to isolate the system? So let's say like this. So this is not on the exam, and this would be a little bit weird, but here's an example problem. So say the spring's natural length is here, right? And this is the mass m, and this thing is floating in free space, right? It's magically held outside of its equilibrium position, and it's released. What's going to happen? Right? So on the final exam, we could ask, how will the mass move? You'd say, oh, it undergoes simple harmonic motion. And then we would say, does this thing move? Right? Does that thing move? And you'd have to say, actually, that has to move. Because this is an isolated system. It's sitting there with its momentum is zero. Right? Momentum is zero. Suddenly some little lever, internal mechanism, releases the mass. And if this thing starts moving this way, to keep the momentum zero, this whole thing would have to move that way. Right? They would have to move together, and they would move in a way where the center of mass would stay still. Okay? Not on the exam because it's about springs and oscillating motion, but you see the idea. Okay? Then you might say, well, if you set this on the table on a frictionless surface, wouldn't the thing still have to move? And the answer is yeah. You would actually be pushing the earth. The earth and the mass would be kind of going, but the earth is so heavy you wouldn't notice. Okay? But if their masses were kind of similar, you could kind of see these two things vibrating together. Okay? So you got to think about conservation of momentum, whether something is isolated or not. If it's not isolated, you could think of it as, if this is the isolated system, then the spring is applying an impulse to the mass. If this is the isolated system, you acknowledge, actually, this will move. You could go either way. All right. We could even do, real quick,